So yeah, today I'm going to talk about looking at the submarine channel element outcrops in oblique view. And one interesting aspect of this is that this outcrop has a lot of three-dimensionality, so we both get a strike view and an oblique dip view, and we see some of the same depositional architectures in both those views. So to set the scene, we're here in Southern California. We're about 80 kilometers north of Los Angeles and in an area called Lake Piru. And these tertiary units are exposed at Lake Piru. And we're going to focus on the upper Modelo Formation, which consists of submarine channel complexes. And so if we zoom in on this inset, we see that Piru Creek has carved a really nice outcrop, and there's a pinch out of the sands in the channel element to the north and to the south, and we have a 90-degree turn in the outcrop here, which, and if we put the paleocurrents, most of the paleocurrents are bidirectional, but the unidirectional paleocurrent measurements are all southward. So this section of the outcrop is actually a slightly oblique down dip view, pretty much parallel to the paleo current. And this would be a strike view, which gives us a good look at those depositional architectures. This is the outline of the drone photomosaic that we collected, and I've split it into 3 panels to give you a closer view of that in a couple of slides. So we're not going to go into too much detail about the sedimentary facies, which unfortunately I think Bouma would be disappointed in. However, due to time, we can just give you a summary. So the channel element has the kind of classic mud at the bottom that becomes more sandy, and then you have these 2 thick sand packages, and which are thickest here in the middle of the channel. And we have a somewhat unique situation in that this purple unit here is a siliceous mudstone. So the Modelo Formation is correlative to the Monterey Formation, which is a diatomaceous siliceous mudstone. And so this charity layer gives us a very good indicator of hemipelagic deposition, which would make this an abandonment surface. So if we start from the north in the photo mosaic, and you can see that the primary channel form surface, so the basal surface of the channel, we've interpreted just above this sand package here, which correlates all the way to an underlying channel element, which we'll see in the south panel. And we also have another secondary channel form surface that comes through here, which we can look in more detail. This photo down here is me standing at this location and looking back onto this face. So standing at the margin and looking back at this face. And you can see that the sands are very thin here. They're only about a ½ meter thick, and they thicken significantly around this corner. And this corner has been eroded, so some of these units are missing a little bit. This is a geologist for scale standing right on this recent unconformity. And you can see that the secondary channel form surface separates these amalgamated sand packages from the underlying chaotic sand and mud packages. And although this unconformity cuts this out here, this orange unit is not present on the other side. So we know that it pinches out somewhere where this has been eroded. If we move into the middle of the photomosaic, we can see that the sands are thickest here. There's a lot of amalgamated sands in this lower package. And so we interpret this as the axis of the channel element. And there's evidence of these backstepping scours that are filled with pebbles that we think is evidence of cyclic steps. And if we move to the south, you can see that these two sand units thin significantly and eventually pinch out south of section 9. One thing to note is this sand that we've put the primary channel form surface on top of is correlative to this channel element here. However, there's another channel element above that that means that this main channel element has eroded into it and deposited here. If we zoom in on this interesting area here, we can see this secondary channel form surface separates amalgamated sand from the underlying chaotic sands and muds. And this secondary channel form surface is an erosional surface, and it has quite a bit of relief on it. It's almost 10 meters in this area, and it's very undulatory. So although we're kind of looking at an oblique view through this channel, we can still give some estimates of the dimensions. We know that the paleo currents are heading south. So if we give just a simple estimate of, we know that the sand is thickest here in this middle section. So this is the axis, and it thins on either side. So we think there's some sinuosity to the center line of the former channel. So if we just draw a simple axis down the middle and then draw the margin on the other side, we can see that the pinch out is, these two pinch outs are along the same margin. So this is the up dip and down dip pinch out along the same margin. So if we draw a simple line between those two, it gives us a half channel width of 275 meters. So if we multiply that 2, that gives us a channel element width of 550 meters. And if we use the channel element height of 29 meters, it gives us an aspect ratio of 19:1. We wanted to compare it to other publications, so we plugged it into Cullis et al.'s power law relationship, and we plugged this height in, or this thickness in. It gives us an estimated width of 575 meters. So we think we are in agreement with other published channel width elements, or channel element widths. So going back to the dip versus strike view, this is an example from seismic data from the Niger Delta channel from Gilbert et al. 2015 and 2017. And if we look at a cross-sectional view through a channel, you see that this typical concave up with terraces and the margin on the edges. But if we look at a down dip view through the center line of this channel, we would only see the channel floor, the base of the channel. We wouldn't see any of these things. However, in my outcrop, it's more of a straight line that's slightly oblique through this. So we do see some of the same depositional architectures that you would in a strike view. This surface, it may have some more erosion on it, which may be to do with some sinuosity here, but basically we have the same look to the depositional architecture, albeit extended a little. Other people are looking at this as well. So Gilbert et al. This is a figure modified from there that has a really nice oblique view through this modern channel. And you can see these different colors represent different time steps. So they're different sediment packages. There's a lot of compartmentalization, and a lot of the same, depositional architectures that you would expect in a strike view of a channel. Here's another example from Nesbitt et al. And this is a down dip view through an outcrop of the Nanaimo. And you can see that if you follow this red erosional surface, you see a lot of the same depositional facies changes, rapid facies changes that you would expect in the strike view are present in the down dip view as well. And this is the model from my figure, and we can see that if we look at from the abandonment surface down to the base of the sand, it's about the same scale that they were looking at in the Nanaimo. So we kind of think about the strike view of the channel being the more important aspect of porosity and permeability changes or facies changes, but I think the down dip view is maybe equally as important for water floods or reservoir models to think about how these are compartmentalized and how they're going to affect production. So just to close, the channel element width of 550 meters yields an aspect ratio of 19:1, which is kind of in agreement with other estimates of channel element width. And we have a unique situation in that the siliceous mudstone is a great indicator of hemipelagic deposition and therefore marks a nice abandonment surface here. And the main point is that strike and dip views, or slightly oblique views, do have similar facies architecture, and so they may be a little bit elongate, but they could be equally as important in a reservoir model. And that is all.
Thank you very much for that documentation of this very interesting field case. So please put your questions in the question box. We have some time for questions. While they come in, I guess my opening question would be, you state that this is a steep margin. So what are the indicators that this is in fact a steep margin, and how do you classify steepness in this sense?
So for some reason I can't share my webcam. It's asking me to and I can't, but so I apologize for that. But maybe this is a good time to plug the paper that will potentially come out pretty soon. This is just a little snippet of the information that's coming in that paper. But so this was a strike slip basin, the Ventura Basin, and it was bounded on either side. Well, think of the outer continental borderlands. So we know just from the amount of sediment that was deposited here that it was a very steep basin side. The fault, the San Gabriel Fault, which was the eastern boundary of this basin, was only about 6 or 7 kilometers away. So it it went from near sea level to very deep in a short period of time.